Hello, friends. Now we're going to look at using a derivative to minimize or maximize, to find a minimum or a maximum solution. And the mins and the maxes for any derivative problem, those are always going to occur where the derivative is equal to 0. So I specifically like this problem because I think it's interesting to not always do business-related problems. Sometimes we can do science-related problems, but also we have a choice. We have to choose between either the product or the quotient rule. So let's read the problem. Using the data collected by zoologist Rito Zak, the work done by a crow to break open a whelk, we have some pictures of whelks there, can be estimated by this function where h is the height in meters from where the whelk is dropped, and w represents work. So this is my work function. One thing you may or may not know is that crows are very, very smart animals or birds, one of the smartest birds. So they have actually kind of figured out the optimal height from where they can fly up into the air and carry this heavy whelk with them, and what is the exact right height that they have to go to where they can drop this whelk and it will break and they don't have to pick it up and drop it again. So the crow figured out what the perfect height was to minimize the work, and we're going to do that as well. So the first thing we're asked to do here is to find the derivative of w with respect to h. So w is my dependent variable, my output variable, and h is my independent variable. This is my x, my input. All right, so it's like x and y. Instead of dy dx, we have dw dh. So the derivative, the rate of change in work with respect to the height. And of course, that should make sense because if they only fly up a little bit, they're not doing much work, but it's probably not going to break when they drop it, so they've got to do that more often. Whereas if they fly up too high, they're doing more work than they need to. So we want to find that max, or that magic height, I should say, where the work is minimized and they drop it and they know it's going to break on that first try. Now, if we look at this problem and think about finding the derivative, you might notice we have a product here. So we have a product. I have this first piece times h. I also, inside the problem, I have a quotient. So what do I need to use? Do I need to use both my product and quotient rules? And you can, but if you always think of and look for that algebraic option, in this case, to distribute, to multiply, we're going to be able to simplify what we're looking at. So I'm going to rewrite my problem, and I'm going to say that work is equal to h times 1 is h plus 20h over h minus 0.93. So now when I look at this, I have two terms, if you will. Because I've distributed, I have two terms to differentiate. This first term is going to turn into 1 when I take the derivative, and the second term, that's where I'll use my quotient rule. So these problems, it's all about, making sure when you look at the problem that you try to use your algebra to simplify first if you can. So I'm going to take the derivative with respect to h of my function I found. W equals h plus 20h over h minus 0.93. So differentiating here, the derivative of w with respect to h, that first term, the derivative of h with respect to h, that's what we're finding there, the derivative of h with respect to h, you can think about that. That's the same as dh over dh. That's equal to 1. And then for this next piece, we're going to use the quotient rule. So you'll notice I'm kind of highlighting here. We have a numerator and a denominator, or a top and a bottom. When we think about our quotient rule, we have a top and a bottom, a t and a b, or you can say n and d, whatever you want to think about it. But I think about t for top and b for bottom. We have bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I've got bottom h minus 0.93 times the derivative with respect to h of the top, which is 20h, minus the top, 20h, times the derivative with respect to h of the bottom, which is h minus 0.93. And of course, that is all going to be over that denominator, h minus 0.93 quantity squared. So I've just applied my quotient rule. Let's see, so now I have 1 plus h minus 0.93, that's not going to change. The derivative of 20h is 20 by the power rule, minus 20h, and the derivative of h minus 0.93, the derivative of h is 1, the derivative of 0.93 is 0, and 1 minus 0 gives me times 1. And of course, I do not need to write times 1 there, so that evaporates, or this piece is equal to 1. All right, so now we have all of that still over the bottom squared. Let me remind you, we do not generally FOIL that bottom out. We normally leave it as it is because sometimes we have those factors that cancel. So let's see, we have dw dh equals 1. I have plus 20h, 20 times negative 0.93. That's going to be negative 18.6. And then, of course, we still have this minus 20h here. So that's all over the quantity h minus 0.93 squared. 20h minus 20h, those are going to cancel each other out. And my derivative of w with respect to h, or the rate of change in work with respect to height, is now equal to 1 minus 18.6 over h minus 0.93, that quantity squared. So that's my derivative. Now I'm going to clean this up, and we'll go back up and finish the problem. So here's my derivative, which tells me the rate in change, how my work changes with respect to how far I fly up. So by part B, one can show that work is minimized, and we talk about this a lot more later, but work is minimized when we set that derivative equal to 0. So we want to find the h value that minimizes w. So in order for us to do that, in order to find this minimum value or maximum, we're going to set that derivative equal to 0. So 0 equals 1 minus 18.6 over the quantity h minus 0.93 squared. Now I have two terms here. Since this term is negative, I'm going to move it to the other side of the equation. 18.6 over h minus 0.93 squared is equal to 1. At this point, treating that 1 like it's over another invisible 1, we'll cross multiply. 18.6 equals h minus 0.93 squared. At this point, we're dealing with a quadratic equation, and we're solving a quadratic equation equal to 0. Now, we can FOIL this out, and we could use the quadratic formula if we wanted. But since it's already in factored form, I'm going to use my square root principle here. So I'll square both sides, or square root both sides. The square root of 18.6 equals h minus 0.93. Now, keep in mind here that the square root of 18.6, when I used that square root to solve, I must write plus or minus in the front. So my last step here is going to add that 0.93 over. So I have 0.93, it's positive, plus or minus the square root of 18.6 equals h. Now, because we have this plus or minus in here, we have two h values. If I solve each of these equations, I'm going to get that h is approximately either 5.24277 or negative 3.38277. Now, let me ask you, can we have a negative h value? What does h represent? H represents the height in meters. So this represents 5.24 meters, rounding to the nearest hundredth, or negative 3.38 meters. Do we have a negative height? The answer is no. That's an extraneous solution in this real world problem. So that means the height, which minimizes work, is 5 and essentially 1/4 meters. So the answer for B here is 5.24 meters. And again, I'm not certain, what the problem is going to ask you to round to on the homework, but always just pay attention to those little blue boxes when you're working on the homework that tell you where to round, where to stop rounding. Now, interestingly, Zach, the zoologist, he's a zoologist, I believe, right? Yes, the zoologist, he observed these crows dropping the whelks from an average height of 5.24 meters, or 5.23 meters. What does this imply? What does this make you think? The crows figured out how to do the least amount of work in order to break the whelk and get that disgusting snail inside. So I just think this is a real nice problem because one, we get to kind of, think about science and biology, but also we had a choice to make here at the beginning, and we used some algebra to distribute that h to both of my terms in the parenthesis, and then I didn't have to use both the product and the quotient rule. So when you start these problems, if you can, please try to rearrange them at the start.